Hello everyone. So we are going to talk about continuous random variables. In this video, we will learn specific properties of continuous random variables such as CDF, PDF, transformations, expectation, variance, mode, median, percentile, and some application insurance. In next module, we are going to talk about some specific continuous probability distributions such as normal, exponential, and some other continuous probability distributions. So random variable x is continuous if possible values basically consist of either single interval or real numbers or union of disjoint intervals. So basically remember that random variables function from sample space to in this case real numbers, or you can say a to b, some interval or union of disjoint interval. So if that happens, then the random variable x is called as continuous. If you remember discrete random variable, the way we define it's a function from sample space to integers. So this one is actually countable infinite. So or you can have countable finite. Now in here, the random variable can take uncountably infinite. It's uncountable and infinite possible values. For example, when we toss a coin, we define something like this. If it is head, you say it's 1. If it is tail, it is 0. So it's a finite possible values. For example, in this case, let's say you are measuring weight. Then you have infinite possible, uncountable basically, uncountable possible values for weight. So so the map would be then into the real numbers or interval. For example, human weight may be between 0 to let's say 400 pounds. So then that would be a range of possible values. One of frequent continuous random variable you will see is time. Whenever we are measuring time, it becomes a continuous random variable unless you convert it to discrete by using discretite version. You can divide it to segments and then you can make it discrete. Otherwise, it's usually continuous random variable. So here you can see the cumulative distribution function for random variable x. This definition is same for any kind of random variable. So for discrete, continuous, regardless what type of random variable, we always use this as the definition of CDF. Then here you can see some properties of continuous CDF of continuous random variable. Something I want to point out here, you see the limiting version. That's because these are continuous random variables, so you may need a limit to get this value. So when x goes to infinity, it approaches to 1. When x goes to negative infinity, it approaches 0. I can draw a sample CDF. So let's say this is a random variable x taking values, and here is the CDF. You can have something look like this. So you can see when x goes to infinity, approaching infinity, it's approaching to 1. When x goes to negative infinity, it's approaching to 0. So that's why sometimes you need the limiting limit approach. And then here you can see how to get the probability, random variable x in between a and b. That's because you can write this as probability x less than or equal b minus probability random variable x taking value less than or equal a. Then this becomes fx b minus fx a. One of properties of a continuous random variable is at a single point its value equals 0. This is not true for discrete random variable. For example, if you take Bernoulli, random variable, let's say it's y, you will have a situation look like this. Probability y equal 1 is, let's say, 0.7. Probability y equal 0 is 0.3. So you can see at a single point, for discrete random variable, it is not 0. But for continuous random variable, those are 0. And implication of that is all of these quantities going to be same, whether greater than or equal, less than or less than equal. It doesn't matter if x is continuous random variable. Now you have to be careful. So this is not true anyway for discrete random variable. Okay, for example, let's say x is binomial, and with, let's say, n equal 10. Okay, number of trials are 10. So then if I try to write probability x equal less than or equal to, that is not same as probability x less than or equal to, because this is basically probability x equals 0 plus probability x equal 1. But this one is probability x equals 0 plus probability x equal 1. But now you have one more, probability x equal 2. So these two are not same. But in the continuous random version, they are going to be same. Now you have to be careful. Sometimes you will see random variables. They look like continuous, but they are not really continuous. For example, I can define random variable look like this. X equal, we are going to talk about this uniform between 0 to 2 with probability 1/2, and then 1 with probability 1/2. So if you have this kind of distribution, then basically you will have a, let's say, um, so you will have a mixed distribution. So these are basically, they are not continuous, they are not discrete, they are mixed distributions. So you have this probability mass at some point. So then this property is not going to valid for this kind of distribution. So be careful. If they sometimes look like continuous, but they are not really continuous random variable. They are mixed random variable. Now, when you have CDF, you can always define density functions. So here you can see the density function, how it's defined. If you know CDF, you differentiate respect to x, and then you get the density function. If you know the density function, you can integrate and you can get the CDF. So basically, you have CDF and PDF. So you can get PDF from CDF by differentiating, and you can get the other one by integrating. Another thing I want to mention here, we call the probability density function. Earlier, we talked about probability mass function with the discrete discrete random variables. With continuous one, you will have probability density function, PDA. So here I listed few properties of probability density function. One thing, it is non-negative. And when you integrate from negative to positive infinity, the value is going to be 1. And then, by the way, this is for all x. So at some point, it can be 0. Okay, so example, I can create a density function look like this. So here density is 0. So this is A. Okay. But it's never going to be negative. Okay. So that's why it says non-negative. Now, when you integrate from negative to positive infinity, so basically you know that integration can be interpreted as area. So the area under the curve, total area under the curve is going to be 1. So this is very similar to what we learn in discrete random variable. Probability x equal x over all x is basically 1. Total probability is 1. Then the other one would be probability between probability that random variable take value between a and b is can be obtained using this integral. So for example, let's say I have a normal distribution and I want to find the probability that random variable take values between a and b, and this is f of x, then I would integrate from a to b, area under the curve between a and b. Now, one of implication of this one is something we saw earlier. At a point, probability x equal a, that's going to be 0. So we are going to do a few problems now. So here you can see a modified SOA problem. Let's do this together. This one says the lifetime of a machine part has a continuous distribution on the interval 0 to 40 with probability density function f of x, where f of x is proportional to 10 plus x to the power negative 2 on the interval. Find the density function. So we know that a density function is proportional to this quantity. So that means density function is equal with some constant c times 10 plus x to the negative 2. So when it says find the density function, what it really asking us to find c. Okay. We have to use properties we learn. It says one of properties of density function is when you integrate from negative equals to infinity, the total probability is 1. So if I integrate negative infinity positive infinity this function, it should give me 1. So if I apply this, since the interval is limited between 0 to 40, if I integrate c plus c times 10 plus x to the power negative 2 dx, I should get 1. From there, I'm going to solve for c. So let's do integration. So this would end up c times 10 plus x to the negative 2 plus 1. So this is basically negative c. So you can substitute values for x and then find the c. So this would be negative c, 1 over 50 minus 1 over 10. So that would be 4 over 50. So that would be c equal 50 divided by 4, which is I think 12.5. So now we know the density. So that's basically 12.5 times 10 plus x to the power negative 2. Find the CDA. So if you go back to the formula, you can see the CDF is defined using this formula. So I can write x equal so this goes from 0 to some t. Yeah, I'm assuming t is less than 40. If it is more than 40, then it should be 1. So let me first write this way. So this would be, let me write t. Okay, so that would be f x dx. So that would be 0 to t, 12.5 times n plus x to the negative 2 dx. And when we integrate, this would be 12.5. I'm just going to use the result in here. So it would be basically 1 over 10 plus x. 0 to t, which would end up as 1 over n plus t minus 1 over 10. So that would be 12.5 t divided by 10 times n plus t. So now we can write more correct way. This would be, let's say t. It would be 12.5 t divided by 10 times n plus t if t belong to 0 to 40. It would be 0 if t is less than 0 and 1 if t is more than 40. Calculate the probability. So this probability, you can use the complement rule. That is basically 1 minus probability x less than or equal to 20. Now you know the CDF. So this is basically fx20. So the CDF value is given, and then you can use that value to get the answer. You can just substitute this as 1 minus 12.5 times 20 divided by 10 times 10 plus 20, and then get the answer. So here is another SOA problems. This one asking us to find the CDF. But before that, let's check whether this is proper density function. We know that if it is proper density function, then when we integrate from infinity to infinity, f of x dx should be 1. So let's see whether that's going to be true. So, so I'm going to integrate from -2 to 4, since everything else is 0. Absolute of x divided by 10 dx. And I want to check whether that's going to be equal to 1. So this one I can break -2 to 0. So we know that absolute value of x is defined as 1. It's negative x if x is less than 0, and x if x is more than or equal to 0. So this one would be negative x divided by 10 dx, then plus from 0 to 4 x divided by 10 dx. Let's see whether this is going to be true. If not, then we have to make a correction to the problem. So this would end up as negative x square over 20 from -2 to 0, plus this one is going to be x square over 20 from 0 to 4. So this side you have negative, then you have 0 minus 4 over 20, plus here you have 16 minus 0 over 20. And that would end up as 20 over 20, which is 1. So this is proper PDF for continuous random variable. I just check. I just want to make sure that this is correctly defined, because it's a modified problem. Sometimes there may be a mistake. Now, since we know that it is proper CDF, we can calculate the CDF now. So CDF, it is, let's say, fxt, that's defined as negative infinity to t fx dx. So assuming t in between -2 and 4, I can write this as -2 to t fx dx. Okay, I'm assuming t in between -2 and 4. Okay, if it's less than -2, the CDF value will be 0. If it's more than 4, CDF value will be 1. Okay, so that's why I'm assuming it's in between -2 and 4. So I can integrate -2 to, so now let's assume um, it's in between, it's less than 0. If it's less than 0, so would have the CDF value as -x divided by 10 dx. So here the assumption is t is less than 0. Okay. So I need to divide it to uh, two separate portion because we have absolute value. So that would end up as negative x square over 10, 20 from negative to t. That would be negative t square minus 4 over 20. Now, if t in with more than 0, so if t is more than 0, then I would have negative 2 to 0, absolute value of x divided by 10 plus 0 to t, absolute value of x divided by 10 and dx. This is fxt. So that would result negative x over 10 dx plus here it would be 0 to t x over 10 dx. So this would will be negative square over 20. This would be x square over 20, but from 0 to t. And when you substitute, that would result um, 0 minus 4 over 20 square t square over 20. So that would be basically 4 over 20 plus t square over 20. So now we can write the answer. F for xt, this one would be 0 if t is less than -2. In between, it would be t square minus, actually it should be 4 minus t square because I have the negative sign in front. So this would be 4 minus t square over 20. If it is between 0 and less than 4, that would be 4 over 20 plus t square over 20. And if it is more than 4, that would be 1. So you can write the CD. Now here you can see the calculated probability between -1 and 3. So we can use the formula -1.5 to 3 fx dx. Of course, you have to break it to two part 1.5 to 0 fx dx plus 0 to 3 fx dx, and you can do the integration. So here's another example from set of factories. In this case, you can see the value V of claim is made in 1 year described by this formula, where Y is random variable density. And we want to calculate conditional probability, V exceeding 40,000 given that V exceed 10,000. So this one asking calculate V exceed 40,000 given that V exceed 10,000. So if I use the conditional probability, this means probability V more than 40,000 and V more than 10,000 divide by probability V more than 10,000. Now that is basically probability V more than 40,000 divided by probability V more than 10,000. Probability V more than 40,000 mean you need to integrate 40,000 to. Now let's substitute for V. I think that make it easier. V is basically 10,000 miles. So if I substitute that, 100,000, not 10,000, 100,000. So that would be probability Y more than 0.4 given probability Y is more than 0.1. So this one we can calculate because we have the density function for that. So that would be integrating from 0.4 to 1 Fy dy over integrated from 0.1 to 1 Fy dy. You can substitute the density function. So 0.4 to 1. I have k times 1 minus y to 4 dy divided by 0.1 to 1 k times 1 minus y to 4 dy. So k cancel out. So you can see that actually we really don't need to find k. If you really want, you can find k using this formula, negative positive infinity Fy dy should be 1. We used that in an earlier problem. From that you can get k, but you can see you really don't need that because you can cancel out k. So here you can see it's going to be 0.4 to 1, 1 minus y to 4 dy, 0.1 to 1, 1 minus y to the power 4 dy. So this end up as 1 minus y to 5 over 5. And that would give you basically if you substitute y equal 1, that would be 0. Then 0.625 over 5. Then on the bottom you will have 0.9. So basically 0.6 or 0.9 to 5. So this one give you another question. So you can see if x is less than 0, the value is 0. If x is in between 0 and 10, the CDF is x divided by 10. If it is more than 10, it would be 1. Show that fx has properties of CDF. So you can calculate what's going to happen limit x goes to infinity, f of x, is it 0? Limit x goes to positive infinity, f of x, is it 1? Is fx non-decreasing? You can go back to the slide and check all the properties of CDF. So these are the properties. Find the PDF. Basically, you differentiate. So fxx, that would be 0 when x is less than 0. In between 0 and 10, it would be 1 over 10. When you differentiate x over 10, it would become 1 over 10. And then it becomes 0 when x is more than 10. So actually, it's a uniform random variable. If you graph this, you can see between 0 and 10, the density is 1 over 10. Okay. We have a real name for this kind of random variable for the uniform. Find probability x is less than 1, more than 1. That's 1 minus probability x is less than or equal 1. And I can use the CDF. So x is less than 1, that becomes f 1. That's basically 1 over 10. It is 9 over 10. And you can calculate the conditional probability. This is probability x more than 7.1 and x more than 6 divided by probability x more than 6. So that would end up as probability x more than 7.1 divided by probability x more than 6. Now, how do I get this probability? That's 1 minus using CDF. How do I get this? Is 1 minus fx6. So that would give me the values 1 minus 7.1 over 10, 1 minus 6 over 10. Now you can get the answer. Graph the PDF and CDF. So I really graph the PDF, and I would encourage you to graph the CDF and see how it's looking. So here's another SOA problem. This one says an insurance company insures a large number of homes. The insured value X of randomly selected home is assumed to follow distribution of density function. Given that random selected home is insured for at least 1.5, calculate the probability that it is insured for less than 2. So I want to calculate probability X is less than 2 given that it is more than or equal 1.5. So again, we can use the conditional probability formula. This means X more than or equal 1.5, and so that means basically probability X should be between 1.5 and 2. And we know how to get the probability. You integrate between 1.5 to 2 f of x. In x more than 1.5, you integrate from 1.5 to you can see that if x is more than 1, so it can go all the way to infinity. And so now it is basically integral problem. You are integrating 3 times to the power negative 40x divided by 1.5 to infinity, 3 times to the power negative 40. So 3 to 3 cancel out. And then we will have integral. So you will have that give us 1 over x cube, 1 over x cube from 1.5 to infinity. So so that would be 3 to 3 minus 1 over 1.5 to 3 divided by, when you substitute infinity, it gives you 0. So it's negative 1 over 1.5 to 3. So that's basically 1 over 1.5 to 3 minus. They simplify and you can get the answer. So I'm going to skip this problem. Please try it, and if you don't know how to do it, please contact me. That is the first video of this module. Next time we will meet and discuss about transformation, expectation, and variance.